So yes, first of all, I want to thank all the organizers for Forum Farge for having me here today, because it's quite an honor for me to talk on the International Color Day, being a previous student in color science. So it means really a lot. And yeah, so this is the talk for tonight that with Peter we decided to have. So it's a non-invasive pigment analysis and the case of the Useberg Viking textiles. So to start off, a little bit more about myself. I come from Agliana, which is a very small town in Tuscany, not too far from Florence, and also not too far from Carrara, who Eric mentioned. It's about like an hour ride. And I've been studying in Florence for the start of my academic career with a bachelor in optics and optometry. And then I moved to study color science with the Erasmus Mundus master, which is called COSI, Color in Science and Industry, for which I traveled a bit all around Europe, or at least 3 countries, Saint-Étienne in France, Granada in Spain, and then I ended up in Gjøvik in September 2019, and I think I quite liked it here, so we decided with my supervisors to continue with the PhD project, which is at the moment entitled Spectral Imaging and Analysis in Combined Visible Near Infrared and Shortwave Infrared for Cultural Heritage. It's quite a long title. We will try to trim it down. And so for today, I wanted to start by giving a very broad definition of cultural heritage, because for our perspective, pigments are mostly found in cultural heritage artifacts. And for the analysis, we need to understand what cultural heritage is. So the UNESCO gave this very beautiful definition, which for cultural heritage is intended the legacy of physical artifacts and intangible attributes of a group of or society that are inherited from past generations, maintained in the present, and bestowed for the benefit of future generations. So that means that if we want to understand and study something that was created in the past, we have to do it in a sustainable way that doesn't affect the way that people in the future will look at the same object. Long story short, we don't have to damage the artifacts while we study them. And this wasn't really too trivial in the previous years, or at least in the previous centuries. But now it is a clear point. So there is the beauty of an analysis that is contactless. And we can divide the techniques that are analytical in cultural heritage into trunks, let's say. We can have punctual analysis, for which we have a painting. And for example, we want to understand some properties, and we go point by point and we scan a single small area. This might be familiar to those of you who have used colorimeters or spectrophotometers. So we go in a specific point and we extract some information. This might be a spectrum. It can be a single value, or it can be a triplet, like an RGB, 3 points of RGB. But then you go to the next region of interest and you repeat the measurement. So you understand that this is a maybe very precise way of analyzing an object, but it's probably not very efficient if you want to have information about larger areas. So that's why let's say, trivially, we go to the other part of the analysis, which are raster methods, which are imaging techniques to bring it shortly. I mean, if, for example, we can have an infrared camera taking pictures of a painting, and then we can analyze, for example, under drawings below the layers of paint. But in the case of my project, the technique that we use for imaging is indeed spectral imaging, which is non-invasive because we do not touch the object, and non-destructive because it is sustainable enough to do not have damage on the painting due to high energy radiation. And this technique can merge the benefits of a normal photography with the technique of spectroscopy. So with spectroscopy, we can extract the information about a determined material. That can be a radiant spectrum, a reflectance spectrum. In general, is a spectrum over wavelengths or over time over their other quantities. And with this particular instrument, we can scan the image line by line. You can see that red line that will move across the field of view of the painting. And for each line, we are able to see the values along the spectral dimension, so the wavelength. There is the electromagnetic spectrum ranging, for example, in the visible from the violet to the red. And then by moving the object, in this case, we can acquire the whole camera, we can acquire the whole object. And then you might have heard terminology if you have ever come across spectral imaging, like multispectral imaging, hyperspectral imaging, ultraspectral imaging. And then you might ask yourself, what are those? What is the, if there is a definition that is able to separate them? Well, it is not really clear. Still, there is a little bit of confusion, but we can look into some factors that are able to differentiate between these techniques. One of them is to look by the number of bands. So in our image that is formed, how many planes of our image we have. Most scientifically, we would just look at the bandwidth, so the distance in the spectrum between the bands. And there is an unofficial limit that is set to 10 nanometers, for which we will call an image hyperspectral. So practically speaking, if we have a camera that is looking into the visible range, if we have around 20 channels, 20 bands, then we will start probably to talk about hyperspectral imaging. And then also we will ask, is hyperspectral always necessarily better than multispectral? Of course, it will provide us a lot more of information because we will be able to sample the spectrum at a higher frequency. But due to the construction limits, we cannot have the same resolutions. So if you really want a high spatial resolution, then you should probably go with a normal camera or with a multispectral camera, because it's there is a construction limit with the way the sensors are built, that you cannot have at the same time a super high spatial resolution and a super high spectral resolution. And this is actually what my project is working at the moment, because, for example, we have that infrared cameras do not have the same spatial resolution of visible cameras at the moment. So what I'm trying to do is to bring these resolutions to match. But then moving into the pigments, we are lucky enough when we go and look at the painting, we are lucky enough to know that pigments, wherever, let's say, you put them, carry with them a sort of passport that it's for which you're always able to recognize them. And this passport is their spectral signature. And in particular is the reflectance spectrum. So reflectance is a quantity that is material dependent, and you can be able to have this quantity if you have information about the instrument that you're using, and if you have information about the light that is present in the scene, because the light goes, arrives on the painting, it interacts with all the materials, pigments, binding media, and canvas, and then it's reflected to the camera. The camera on its own has some spectral sensitivity, and then it will provide some raw values. But then if we are able to, if we know, and usually we do know, the properties of the camera, and we know what is the spectral power distribution of the light, and there are methods to know that, we are able to get the reflectance of the object that we're looking at. So we will be able to have the spectrum, let's say, of the pigment cadmium yellow. And if we know how cadmium yellow looks like with the reflectance, we can look through the painting and see with some specific metrics if there are spectrum that are close or that are matching to the spectrum we are looking for. But then, of course, we will not be 100% sure. We will be maybe 80% sure that that pigment is present in that pixel of the image. And then we can ask ourselves if identification is enough. Of course, it is important to know what pigments are in there, but it will be maybe probably more interesting to know how much of a pigment is present in a pixel. So even if I'm let's say 80% sure that cadmium yellow is in a pixel, and let's say 40% sure that vermilion is also in the same pixel, how can I know the proportions of these two? So this is a topic that has been researched for quite a long time, and this is called spectral unmixing. So spectral unmixing is a problem that knowing the spectrum of the painting, let's say, and knowing the spectrum of the individual pigments that you maybe know a priori, you can understand what are the concentrations of those pigments, because those concentrations and those spectra of the pigments are modeled together to give the final spectrum of reflectance. So the very first and still very valuable model that has been formulated was almost 100 years ago by Monk. I'm not going through the model now. This is also the simplified version. But we can also have easier models like the one that is reported below. And so in the end, we can create, by going pixel by pixel, we can create those, in this case, are quite fake, let's say, those are not real, but we can create concentration maps. So for example, let's assume that the first one is the concentration map of vermilion. We can know where the red is more bright. We can know that in that region, the concentration of vermilion is higher. And then where the red is not that bright, we have always lower and lower concentrations. And we can do this for all the pigments that we assume are in a painting. And this brings us to the case study of the Useberg textiles. You are maybe more familiar with the Useberg ship that was found than me. I discovered about this history just recently when I joined this project. And this ship was found almost 120 years ago in the south of Drammen by this group of gentlemen. And this ship was contained in a boreal sort of hill, and it contained a lot of things that were used by the Vikings population that were believed to help for the journey to the afterlife, because this was a burial for two women. And what was one of the most prominent findings in this ship was a series of fragments of textiles which vary in their shape and their status of conservation and the material. And this is what this project focuses about. So we have here these textiles. You can see that some of them are different fibers. The conservation state of the fibers is really different. And also here is not reported the scale, but consider that there are thousands of these fragments, and the smallest ones are the size of a fingernail, even smaller, and the biggest one are the size of forearm, let's say. And so the TextRec project was born last year, and it is aimed at having virtual reconstruction, interpretation, and preservation of the textile artifacts from the Useberg find. And it has 4 main missions that regard the imaging part. One of them is the digitization of the fragments. One is the dye stuff and pigments analysis. One is the tracing of conservation treatments that were done in the last century, because it's not clear and not well documented. And one is the puzzle project, that is a very exciting part of this, that is aiming at putting these fragments together in a way. And this project is led by Kulturhistorisk Museum of the University in Oslo. And of course, NTNU is a partner among other international partners. And in my part of the project, we are having hyperspectral imaging of the fragments. So this is our setup. We have these cameras that are looking down directly to the object. And we have the object sliding across the field of view of the cameras, because they acquire one line at a time. So we know the illumination. We have some calibrated targets there to have the information about the illumination, and we can retrieve the reflectance. Now it's a bit early to present any results about the pigment analysis, because this project was done, the acquisition was done just last month. But here we have an example of how hyperspectral imaging can be can bring more information regarding maybe the composition, but definitely the structure of an object, because we can apply techniques such as PCA, principal component analysis, if you ever heard of it. This is a multivariate techniques that basically divides the information in this very big image that we have, and it's able to determine components in this image and recompose these, for example, these 10 images that are looping, and these images are carrying all the information. And analyzing these different components, we are able to get information both about the structure and the pigments, which of course is what we are hoping to have in the very near future. And here is, for example, one of those channels recolored to highlight some of the structures. And yes, this is it from my side. And thank you again, and I'm open for your questions.